Hello friends, I hope you must have seen the introductory video on the online course titled Risk and Reliability of Offshore Structures. I am Professor Srinivasan Chandrasekharan from Ocean Engineering Department, IIT Madras, who will be coordinating this course for you in NPTEL in online series. The course as discussed in the NPTEL site will be discussed and delivered in 3 different modules. Module 1 will focus on the classes related to probability, plausibility theories, uncertainties and error estimations. This is the first lecture in module 1. In this lecture, we will talk about introduction. So, we are talking about risk and reliability. Now, the interesting part is the application of this will be purely advocated to offshore structures. So, we will talk about the module 1 now. In this lecture, I will give you an introduction to the course and I will also take forward some of the lectures in first module. In this lecture, we are going to talk about details of different uncertainties. However, this module will include different outlines on reliability and risk estimates as related to. We will talk about introduction, we will speak about concepts of probability, we will also talk something on sampling statistics, we are going to discuss about modeling of random variables, we will also talk about the classical reliability theories, we will introduce you the classical reliability theories, we will also discuss about error estimations. This will be the content what I will be discussing in the first module. Today we will start with the introduction to the first module and some important topics related to uncertainties. Regarding the detailed list of textbooks which are required for this course, please refer to NPTEL website. We have given detailed list of textbooks and reference books. We have also listed very important journal papers and conference proceeding papers which may be useful for you throughout the length of this course. So, kindly use them as an additional and parallel support material along with the lecture notes what we will be following in the blackboard and through PowerPoint presentation in all the lectures. This course will approximately have about 40 lectures. We will also give you tutorials at end of each module along with the solutions which will be discussed in the blackboard. At the end of the course, you can also take up an exam which is online certification exam offering a degree or offering a certificate by NPTEL IIT Madras if you qualify the examination with qualifying marks as mentioned in the website. So, if you do not have any clarification and doubts, I will proceed with the lecture. In case if you want to contact me or you want to write to me, please write through the web portal of NPTEL of this specific course after your registration is finally approved by the NPTEL board. So, we will talk about introduction to reliability, explaining why reliability is a very important tool in analyzing offshore structures. Please look at the slide projected on your screen now. Offshore structures actually have varieties of complexities. The one what you see is combination of different kinds of platforms, which has been pictorially shown in the screen now. You can see one of them is resting on trussed legs, which we call as jack-up rigs. The one which you see in the middle is a spar platform. The one which you see on the right top is a typical jacket structure, which shows different kinds of loads that are acting on this kind of structure. The one what you see in the right bottom is again a typical sketch of an offshore platform. The one what you see on the left is an articulated tower with a buoyancy chamber and the ballast chamber indicated in red in color. These pictures will give you an idea that offshore structures are very classical in nature. Now, what are the specialities of these kind of structures? There are many reasons why offshore structures are called as special class of structures. 1, they are unique in the design. And functionality, because you know offshore structures are actually designed according to the functional requirements. There are exploratory platforms, there are drilling and production platforms, there are platforms for processing and storage, what we call as FPSO, FSRUs, drilling rigs, drill ships, tension leg platforms, spar, etc. However, this course does not give you an overview of different structural systems used for variety of functions in offshore field. You can look into the good references listed in the NPTEL website of this course to get more parallel idea about different structures which are used in offshore engineering. So, let us come back to the point. Offshore structures are unique in the design. There is no two similar structure which are used for a same function, because of very specific reason. All offshore structures are unique because there are site specific characterization which makes them unique. So, they are unique in the design, and of course, as I said, they have uniqueness in their functionality as well. Most importantly, they are form driven design. What do you understand by a form driven design? The geometric form of the system commands the design. For example, I will quickly draw a line diagram of a jacket structure and a tension leg platform. Both are typical offshore structures. Let us say this is my top side, which may have a drilling derrick, which may also have a crane boom, which may have some living quarters, which may have an helipad as well, which will be supported on a template system, which is actually the jacket legs, which will be founded using pile foundation into the seabed. This is my seabed. To strengthen these legs, because of the water depth being very large, we also insert bracings, and we call this assembly as typical jacket structure. So, we call this as a jacket platform. On the contrary, for example, there is a water line here, this is my mean sea level. I call this as my top side, and so on. On the contrary, if you talk about a platform which is also used for deep water exploration and production, we have a typical platform called tension leg platform, which has vertical columns and horizontal members, which are pontoons, which are actually supported to the seabed only by tethers, what we call as tendons or simply axially stressed cables. Now, look at the geometry. The top side of course going to be common as similar to this. The functionality is more or less similar because this is also used for oil production and exploration. This is also used for oil production exploration. Now, there is a limitation in water depth for this kind of platform, because for the entire water depth the whole structural system needs to remain intact, whereas in this case the water depth can be much pretty higher because only cables are extended to hold the system down to the seabed. If the cables are disconnected from the seabed, for example, the whole system remains afloat. That is why we call this as a compliant system. So, offshore structures are form driven design. No specific geometry will have commonness for their functionality or to resist their external loads. So, therefore, in this example as we just now discussed, tension leg platforms, what you see on the right here, are structurally or geometrically different from that of a jacket platform. Of course, both platforms may have similar functional requirements. Therefore, offshore structural design is unique because it is form driven, it is not function driven. Therefore, one cannot compare the response behavior of one platform of a different structural form with that of another platform whose structural form is entirely different in its behavior, in its material usage, etc. The next issue is very interesting: construction enabled design. What do you understand by construction enabled design? For example, let us talk the same case of a jacket platform or a tension leg platform. Let us say jacket platforms have been identified in the literature to be useful up to a maximum water depth of about 300 meters. So, if I am going to go for a water depth of about 300 meters, which is indicated as small d in the literature, because capital D will indicate the diameter of the members. Naturally, I cannot have a single material or a single member of this length, because transporting this, fabricating, erecting and commissioning becomes a very tedious job, because I am talking about all these issues in situ in a sea which is 300 meter deep. So, they will be constructed in modules. Therefore, one has to decide what is their crane capacity, what is the barge holding capacity in terms of size of the member, what is the crew capacity which is going to install the member in position, which will decide whether the construction enabled design is feasible. This also makes offshore structures something unique. More interestingly, gentlemen, offshore structures are now focusing towards deep and ultra deep waters for oil exploration As we all understand, the oil reserve in shallow waters is almost exploited. So, people are looking for deep and ultra deep waters. The moment I say deep and ultra deep, just to give you a clue, I am talking about the water depth in terms of 1000 meters, 2000 meters and so high. So, obviously, a structural form which can suffice 300 meter depth cannot be used as it is for 2500 meter depth. As a structural engineer, as an engineering mechanics graduate, we all agree with my statement, there needs to be some major modification in the design or in the structural geometry which can enable the construction feasibility and of course, the survivability of the platform as the platform installation goes deeper and deeper. Therefore, any new offshore structure designed today or will be designed tomorrow or in the near future will also remain as a unique challenge, because the oil exploration is driven towards deep and ultra deep waters. Having said this, let us discuss some classical problems or some special features which makes offshore structures much more interesting. There are some prerequisites to make the offshore structures safe while they remain functional. The most important is, it is expected that the offshore structures should remain flexible, because any rigid system is always tend to attract more forces. The attraction of more environmental forces coming on the system will improve the stress on the members, which results in failure of the members, where the reliability of the existence of the platform functionality can be questioned. On the other hand, if the structure remains flexible, the structure adapts to the environmental loads, which makes the system more interesting. Therefore, I need a flexible system. At the same time, it should also remain robust to encounter the loads. I will also say very clearly environmental loads. There are a variety of environmental loads which act on the structure or offshore structures. I can give a classical examples in detail later, but for your understanding, essentially and predominantly wave loads, wind loads, current loads, earthquake loads, topside loads, accidental loads, shock loads, impact loads, ice loads, we can keep on adding the list. The structure should remain robust to encounter these loads while they remain functionally safe. That is very, very important. Safety is a foremost issue here. So, functional safety becomes a key factor in offshore structural design. However, a geometric form chosen for any specific water depth, however, the system remains flexible and robust to encounter the loads, if a structural system does not remain safe when it is performing its intended function. For example, you may ask me a question, what is that so called intended function the structure should perform? The intended function an offshore structure should perform basically is either oil exploration and production or storage and reproduction, etc. So, while making these functional issues important, the structure should remain safe. So, safety in terms of functional existence is a key factor in offshore structural design, which may not be true in almost all other classical design of structures. Therefore, offshore structures make or made unique in nature. Let us look into other complexities which make the whole analysis or the safety getting challenged. Let us say other issues. There are other issues which can directly challenge the safety of an offshore structure while they are functional. What are these issues? 1. Many new and innovative material are being used. For example, aluminum, titanium and their alloys etc. have become very commonly getting used in offshore structures. Now, one may ask me a question, what is very curious about this? This demands detailed understanding of their mechanical properties. The moment I say detailed understanding of their properties, as we all know, we have been studying steel and concrete as a very common construction material for which more or less almost all characterization of material properties are known to us through laboratory experiments. Whereas, if you take up a new composite material which is being recommended by a designer for a unique structural form in offshore structures, it becomes mandatory for the engineer and the team to understand the detailed mechanical properties of the material at different temperature, at different stress concentration factors, at different load combinations etc. Because the material can fail at critical combination of loads, which becomes very important because safety is a primary concern here when the structure remains in use. The next issue could be variety of environmental loads. The environmental loads, when they get combined, gets more complex and all of them lead to what all of them lead to? 1. The uniqueness of the design, 2. The material advancements, 3. The environmental loads and their complexities will lead to varieties of uncertainties. In physical terms, what do you mean by uncertainty? Uncertainty is a variable or a parameter which is not known to you for sure. You know the value, can guess the value, but you do not know amongst the value from x to y what would be the value of the variable, maybe the material property, maybe the load magnitude, maybe the strength in the member etc. under a given point of time, under the given combination of load, at a given age of the structure. You do not know. You have a very large bracket of this value, but within this range what is that value exactly the material or the member is assuming at that age, at that period is not known to you. This is what we call physically as uncertainties. Interestingly, ladies and gentlemen, if you do not know very clearly what is the value of the material property or the load magnitude at any specific location, time and age etc., it will be very difficult for you to ensure safety of the member and the material under the given combination of forces. If you are not able to ensure the safety of the material or the member or the structure cannot be called a reliable one. So, reliability of offshore structures is circumscribed importantly around a major factor called uncertainty. As a good mathematician, you would have guessed by this time, wherever we have uncertainty in mathematics and engineering, we always use probabilistic tools and statistical methods. You may ask me an interesting question. Under the given mathematical accuracy of numeric modeling, analytical studies, various wave theories, various engineering mechanics solutions available, why still at this age of engineering we say we are not understanding very clearly with certainty about the properties? I will come to an example. Let us take an example of an environmental load. Like for example wind. I will give you a very quick illustration of this. Let us say I want to estimate the wind force on a given offshore member to design the member. We all know when the force is known to me on a given member, when the permeable stress of the material are known to me, I can always find the cross section properties of the member, what we exactly call as a design. We assemble this member, we call the structural geometry, we fabricate the member, we make a platform and commission the platform for oil and gas production and exploration. I want to know the wind force on a specific member. Let us take a member of a specific diameter which we are assuming. Okay. We all know if you do not know the diameter, you cannot find the force. If you have a doubt, let me explain this. Wind force is actually a generation from the pressure which is proportional to the projected area. The projected area is of course a function of the diameter if it is a circular member. So, you have to assume the diameter of the member. When you assume the diameter of the member based upon your engineering expertise, experience, etc., you want to compute the force. Now, you are trying to find out the force which is dependent on velocity, and velocity depends on various parameters like surface terrain, height, time, etc. Let us say I take the velocity of wind at every day 8 a.m. for 100 years, every day 8 a.m. 100 years. I measure the wind velocity for 5 minutes, let us say 8 to 8:05, I measure, I get a history. It is not of course going to be constant, get a history, I get a mean. Let us say the mean wind velocity remain at 30 kilometer per hour, let us say. Now, this data is suitable and valid for a specific location, for a specific time, for a specific geometric interference, for a specific sea climate, for a specific humidity, for a specific height, because this depends upon the height. We all know wind velocity keeps on varying as he keeps on measuring it higher and higher. If you really wanted to measure this on a 2-dimensional array, you can always measure another member and try to find the interference of the spacing of the member on the velocity of the member at this point as well as this point, what we call cross correlation coefficient. Now, if the data is taken at 8 o'clock, obviously if you take one more data at 9, 10 and see, you will find that the mean wind velocity or the speed keeps on varying considering all these factors. So, even for one specific load, for a one specific moment has got so many variables which lead to uncertainty in estimating with a great degree of accuracy the wind load on a given member. Therefore, we can confidently say environmental loads are not completely known. Only some features are known. Let me put it like this. The second issue is the randomness. The randomness in the environmental loads increases the uncertainty. And this will lead to the consequences in many facets of offshore structural design. One is during the planning, during the analysis, during the design, during the construction, and even during the reliability analysis, which includes the age factor. So, at all these stages we need to understand two issues, that is during planning, analysis, design, construction, erection and commissioning, aging factors, etc., I need to know two important things. One, I must know how to accurately estimate, that is accuracy in environmental loads is one issue which I am bothered. Secondly, the construction process itself and the techniques. One can ask me a question interestingly, if one single variety of load has so many complexities and uncertainties, is there any way by which this can be handled in engineering manner in the offshore structural domain? The answer is yes. Reliability is a very interesting tool which is widely accepted to handle such uncertainties very effectively. Many researchers have certified this by applying this to various problems of different complexities. Let us now understand what are the advantages of reliability methods. Advantages of reliability methods. 1, they offer realistic possession of uncertainties. They offer realistic possession of uncertainties. They offer methods to evaluate the safety factors both for loads and material strength. You must have studied limit state design. You must have studied partial safety factors, gamma m for the material and gamma f for the loads. All these partial safety factors are actually evaluated based upon reliability methods. They offer very good decision making process. Or decision making support for more economic design. They also enable analysis. They also enable analysis using different methods of failure. That is very important part in reliability analysis. You can assume a failure state and check whether the member is crossing the failure state or within the limit state of safety. So, you can analyze the system for different methods of failure. You can also expand the knowledge of uncertainty, because earlier you do not know what is an uncertainty. As you keep on knowing it more and more, you can always expand your domain of knowledge in uncertainty. The moment you expand the knowledge, many uncertain parameters in your analysis and design will appear to become slowly certain. They enable optimal use of material, interestingly, they also help you to estimate partial safety factors to account for the uncertainties. Now, one may ask me a question, what is speciality about this? Interestingly, let us say you have a partial safety factor gamma m as 1.15. Now, the number 1.15 is derived based on the material properties of either concrete or steel or composite or an alloy by testing various cross sections under various conditions and estimating the mechanical characteristics and then finding out the safety factor of material strength. Now, without knowing the uncertainties in this variation, a partial safety factor is recommended in the codes, which can be used as a tool to account for uncertainties without even knowing the knowledge in detail about these uncertainties. So, reliability can also act as a silent supporting team which can educate the engineering designer to account for an unknown parameter which he or she has never heard of, but still he or she will land up in a safe design. Interestingly, reliability methods have certain limitations. They are mostly belong to family of probability, to a smaller extent, and family of statistics to a larger extent. The moment I say this, one will be interested to know a stretch of knowledge about this. If you are a mathematician who is a very good knowledgeable person in probability and statistics, you can always doubt a solution based on the knowledge of probability and statistics if you are a mathematician. But if you are an engineer, doubting will not help you. You have got to address the solution. So, reliability engineer who extends the theory of probability and statistics as a tool for reliability analysis needs to ultimately land up in an effective solution for the problem which has got lot of uncertainties. The second limitation could be it explicitly underscores the risk acceptance. Now, I am using a new term what we call as risk acceptance. Interestingly, many researchers said the risk acceptance criteria it is an implicit factor. I think you agree what is an implicit factor? It is inbuilt actually. Any material strength, if you say, take for example mild steel, plot stress strain curve of mild steel, and if you try to find out the sigma y value for mild steel and fix up this value as let us say 250 Newton per mm square, with some certainty you say that the yield strength of the material used is 250 Newton per mm square. If the material does not have uniformity in its manufacturing, in its grain structure, in its cross sectional thickness, etc., all those are inherently taken care of when you do the testing in the laboratory to get the yield value as 250 Newton per mm square. So, there is a risk acceptance of accepting this number as a design value which is implicit, but reliability will show this as an explicit value. So, that is a limitation in the study. Therefore, in general reliability methods actually project project the overall process of analysis design and construction of offshore structures as a probable solution but not an exact solution. So, reliability based design is or will lead to a probable solution of the problem, but if you ask what is the guarantee that the solution arrived as a structural form based on reliability solution is sufficing. What is the guarantee? The guarantee will always remain as a guess, because it is having a probability tag to it. Any probable term is always subjected to its accuracy and tools used for guessing this value. Therefore, to accept this solution you need engineering decision which based on experience. The moment you have a probable solution you will always have a doubt, is there an alternative for the solution or not. The moment the solution is not unique, which has more challenges, which can have suspicious alternatives, then you do not rely on the solution. So, reliability has this as one of the important and serious limitation. Therefore, reliability solutions need to be supported by engineering based experience packed judgments. You cannot accept the solution of reliability theories or reliability problems as such. You have got to apply a tool based on your experience. You have got to correct the solution and then recommend this with of course a factor what we call a safety factor or a reliability index. So, we stop the lecture here. In this lecture we made a short summary of different types of offshore platforms. We said why they are unique, what is form driven design, what are the complexities and challenges involved in their construction, installation, etc., what are the innovativeness in the material and why they are required, Therefore, in the recent advancements, how offshore structures can lead to different levels of uncertainties. If uncertainties are surely present in a given system, how they can be handled? We understood something about reliability. The moment we say reliability can handle these uncertainties more effectively, then we looked into the advantages of these methods. But of course, we also saw serious limitations of this method, which ultimately tells me the solution given by reliability theory cannot be blindly applied on a structural system, but it requires a support, a recommendation which is purely driven by engineering based, experience packed judgment, which ultimately tells me the reliability index of a given system. Therefore, reliability can be used as an assessment tool. For example, an existing structure need to be assessed. You can use reliability theory or reliability engineering as an assessment tool. Reliability can also be used as a design tool, what we call probabilistic based design, performance based design can be used. In either way, the recommendation finally to be made to the board or to the client depends also on the recommendations made by the engineer judgment by the reliability engineer. So, this makes a clear understanding to you. The reliability engineer needs to gain experience in offshore construction design, planning, analysis, commissioning, erectioning, decommissioning, all facets of engineering problems to really understand or really make him as a successful reliability engineer. So, in this course we will talk some of these important tools and software enabled with these tools to make you to understand theoretically the reliability and risk assessment applied to offshore structures. However, to make you a really a good risk engineer, reliability engineer depends on how do you practice this profession with enthusiasm and sincerity and gain experience, so that your decision made on certain issues or basically depend on your practical experience on similar problems. Thank you very much.